Hello. Thank you for watching today's presentation on efficient mouse colony management. My name is Peter Kelmanson, and I'm delighted to share this educational information with you to support your efforts to achieve research excellence. If you have any questions about the content of this presentation, please contact us using the information on the final slide of this presentation. Now, before I get started with today's presentation, I want to share with you some information about the Jackson Laboratory. The Jackson Laboratory is an independent, nonprofit biomedical research institution. Our mission is to discover precise genomic solutions for disease and empower the global biomedical community in our shared quest to improve human health. We advance our mission in three ways. The first is by conducting biomedical research. We have grant-funded research faculty who study the genetics, biology, and mechanisms of human disease using the laboratory mouse as a research model. Secondly, we provide research resources and services to the global biomedical research community. Our resources included a wide array of mouse models known as JAX mice, a variety of contract research services to support mouse-based preclinical research and translational efficacy studies using either your own mouse models or JAX mice, and several databases with freely available, publicly accessible, comprehensive mouse model-related information. The third aspect of our mission is to share our expertise through scientific education and training programs such as courses, conferences, internships, pre- and postdoctoral training, on-site seminars, online learning resources, and also live and on-demand webinars such as the one that you are watching today. Jackson Laboratory receives funding from public sources such as the National Institutes of Health in the United States. A significant amount of our public funding is used to import as many unique and scientifically valuable mouse strains as feasible from the global research community, and then to distribute those models to researchers around the world. Currently, the Jackson Laboratory is the world's largest repository of mouse models. We currently maintain more than 11,000 mouse strains and import hundreds of new strains every year. Annually, we ship more than 3 million mice to researchers around the world. The unsurpassed genetic quality and animal health of JAX mice enable high-quality, reproducible research. As the most referenced and extensively characterized mouse models available, JAX strains empower researchers to jumpstart research studies because our strains come with a wealth of publicly accessible, freely available knowledge about their phenotypes, genetic history, and research applications. The Jackson Laboratory supplies both commonly used inbred mouse strains such as C57 Black 6J and BALB-CJ, etc., and also thousands of unique mouse models. The distribution of commonly used strains supports the development and collection of unique mouse models available only from the Jackson Laboratory, and also our mission to improve human health. Now I would like to briefly mention a few of our online resources freely available to support and expedite your research. The JAX mice database enables searching for our available mouse strains by gene or allele name, common names, or the type of mouse strain like Cree or LOXP flanked alleles, etc. In this database, you will find mouse strain data with extensive information about each strain, including their reported phenotypes and publications referencing that strain. We also maintain the Mouse Genome Informatics database, which is a bioinformatics database curated by scientists who read published literature on mouse genes, mutations, and transgenes, and then enter into MGI curated data in a searchable format. The MGI database includes data on mouse strains that are available not only from the Jackson Laboratory, but also available from other researchers and repositories around the world. Consequently, MGI is a valuable resource to learn about the many mouse strains available that may be candidate models to best support your research goals. The Jackson Laboratory also hosts and supports the Mouse Phenome Database, which is populated with data from an international collaborative effort to collect baseline phenotypic data for most of the commonly used inbred JAX mice strains like C57 Black 6J and BALB-CJ. These data often can help accelerate your research by minimizing the need to collect extensive baseline phenotypic data in your own laboratory. Instead, you can invest your time and resources in validating phenotypic data reported by other researchers. We also maintain the mouse tumor biology database, which is focused on mouse models of cancer and contains data from curated published literature. This database is searchable, publicly accessible, and contains tumor information in mouse strains, and also houses our patient-derived xenograft data. And lastly, we maintain the JACS Clinical Knowledge Base, which is a digital resource for interpreting complex human cancer genomic profiles that may help oncologists and cancer researchers assess cancer therapies based on the genetics of the tumors. Okay, so for today's presentation, I'm going to start by providing some key background information on reproductive characteristics of mice. Then I'll discuss some of the factors that can affect breeding performance. Next, I'll describe the importance of rigorous data collection and good colony management practices. And then I'll finish up by sharing some of the internal studies we have performed at the Jackson Laboratory to assess caging density and enrichment as ways to ensure the health and well-being of the mice that we distribute, as well as help to improve the breeding efficiency of our mouse colonies that produce the mice that we ship worldwide. Let's start with the reproductive characteristics of mice. For most mouse strains, the average gestation period is about 18.5 to 21 days, but can vary based on the strain. The gestation period for C57 Black 6J mice tends to be at about 18.5 days. However, the gestation period for Balb CJ mice is a little longer, usually about 20 days, and even longer for AJ mice at about 21 days. The gestation period is generally consistent among individual mice of each strain, but often there is some variation. The length of gestation can also be affected by litter size. Larger litters tend to be born earlier, smaller litters tend to be born later. Gestational periods also tend to increase as females start to get older. Litter size in mice can range from anywhere as low as 1 to 2 pups for strains that breed poorly to 12 or more pups for strains that breed well, like outbred mice, hybrid mice, or some of the inbred mouse strains like FVB or NOD. Weaning age for most mice is strain dependent, but for most strains here at the Jackson Laboratory, we wean pups at 3 weeks of age or 21 days of age. If we know the pups for specific strains tend to be smaller or more fragile at that age, we may delay weaning until 28 days of age to give them an extra week to put on more weight or to gain more strength. We determine the optimum weaning age from direct experience with the mice. Mice reach sexual maturity between 5 and 8 weeks of age. In general, females tend to reach sexual maturity at 5 to 6 weeks of age, whereas males become sexually mature at an older age, usually about 6 to 8 weeks of age. Based on these typical ages of sexual maturity, we frequently set up our matings at about 6 to 8 weeks of age for many of our strains, especially those bred in large colonies, so that the mice are being mated at the time of their sexual maturity. However, the ideal age to mate mice is strain dependent and should be determined empirically in your own facility. The productive breeding lifespan for most strains is about 7 to 8 months, which is generally the breeding window for the most efficient breeding. For most strains, after 8 months, breeding performance begins to decline, as indicated by litters becoming smaller and less frequent. Therefore, to maximize the efficiency of a breeding colony, you want to keep all of your breeders at ages within that strain's most productive breeding window, and then retire and replace them when their age exceeds the high end of that window. Breeding performance can be affected by a variety of factors, including the genetic background. For example, C57 Black 6J mice have a low percentage of mice that develop postnatal defects like hydrocephalus, which is the accumulation of cerebral spinal fluid in the brain. You can identify those mice by their characteristic dome-shaped head. Malocclusions are also more common in C57 Black 6J mice than in other strains. Some strains have a high fecundity, like BTBR and FEB. And strains that are on a mixed background, like F1 or F2 hybrids, exhibit hybrid vigor, so they tend to be more robust, better breeders, better parents, and produce larger litters. Strain background can also contribute to behaviors such as poor mothering or aggression. Some mutations or transients can also affect breeding performance. There are many mutations or knockouts that lead to embryonic lethality when homozygous. Some mutations can lead to infertility or subfertility. Some mutations can affect mammary function or lactation as well. Mutations or transients can also shorten the breeding lifespan due to the onset of a disease phenotype. As an example, here's a mouse strain which is a mouse model for Huntington's disease. These mice develop a neurodegenerative phenotype and therefore have a shorter breeding lifespan. As another example, the development of tumors in cancer mouse models can impact how long the mice can survive and will be able to breed. If the mutations or transients in your mouse strains affect their breeding performance, you will need to plan your colony sizes with consideration for their specific phenotypes, including the typical age of mortality of your mice in your facility. Environmental factors also can affect the breeding performance of your mice. Mice tend to breed at the midpoint of the dark cycle and need uninterrupted darkness to breed well. Interrupting the dark cycle in a breeding room with lights coming on accidentally can negatively affect mouse breeding performance. Mice are also very sensitive to noise and vibrations and can hear ultrasonic frequencies that are outside the range that people can hear. The noise of people entering and exiting the room, nearby construction, loud equipment, or even ultrasonic noise from computers can all negatively impact mouse breeding performance. Mice tend to be relatively comfortable at the same temperature as people. Temperatures that are too high or too low can affect the mice and their breeding performance. Mice are also sensitive to handling. Handling mice too frequently can cause stress in the mice. For example, weighing mice every day can be stressful to mice and lead to weight loss. Handling your mice as little as possible while maintaining your colonies and performing your experiments helps reduce their stress as much as possible. Mice can also become accustomed to their caretaker. When a caretaker changes, the mice can become stressed, which can lead to a decline in their breeding performance until they become familiar with their new caretaker. Much of mouse breeding behavior is pheromone-based, so any odors that can interfere with pheromones will negatively impact breeding performance. At the Jackson Laboratory, our animal caretakers do not wear any type of personal fragrance while they're handling the mice. Mice also require sufficient nutrition to thrive and breed well. Poor nutrition can negatively impact their breeding performance. The health status of the mice can also impact their breeding performance. If mice are immune challenged by the microorganisms of breeding facility, they may not breed as well. In some strains, you can see some seasonal effects where mice breed better at certain times of the year, like the spring or the summer versus in the fall or the winter. This is an example of 3 different mouse strains that all carry the same exact interleukin-2 knockout allele, but are on different genetic backgrounds. The mortality, colitis, and anemia phenotypes of these mice differ depending on their genetic background. On the mixed genetic background, the homozygous knockout mice develop progressive colitis and anemia. They survive to 4 to 8, 9 weeks of age. On the C57 Black 6J genetic background, the homozygous knockout mice survive to 10 to 25 weeks of age. In a dirty mouse facility, they develop colitis and anemia. On the BALB-C genetic background, the mice develop anemia but no colitis and survive until 3 to 5 weeks of age. On the mixed and BALB-C genetic backgrounds, the homozygous knockout mice die before they are old enough to breed. Therefore, colonies of this knockout on those genetic backgrounds have to be maintained by breeding heterozygous mice, which is less efficient and requires a larger colony. On the C57 Black 6J genetic background, some of the homozygous mice will breed, which will ultimately improve the productivity of a colony of those mice. It is important to remember that the genetic background of your mice can affect the phenotype of your mice, which in turn can affect the breeding performance or breeding efficiency of your colony. Knowing the breeding and husbandry characteristics, as well as the phenotypes of your individual strains, enables you to plan your colony sizes with consideration for differences in breeding performance based on individual strain differences. Even if you have extensive mouse breeding experience, you may be faced with breeding challenges due to your strain's genetic background or phenotype. When working with difficult to breed strains, there are some actions you can take to encourage breeding. First, provide your breeder with a very quiet place in your mouse room, away from doors and from any sort of noisy equipment in the room, like air handling equipment, sinks, computers, etc. Also, as I mentioned earlier, ensure that the breeders are getting adequate darkness and that the dark cycle is not being interrupted. You may need to put a light meter in the room housing breeder mice to ensure that the lights are not coming on during the dark cycle. Additionally, minimally handle the breeders, especially when the females are close to giving birth or soon after they give birth. You may want to delay cage changing until the pups are a few days old to minimize stress on the mother and newborn pups of a cage change, which creates a new environment. It's important to handle the mice with either clean gloves or clean forceps. If you use gloved hands to handle mice, make sure that you clean or change the gloves between every single cage that you handle. Doing so avoids transferring scent from one cage to the other cages. New scents can be stressful to mice and so may interfere with breeding. Exposing a pregnant female to urine from a strange male can cause her to abort. Limiting scent transfer from one cage to another can therefore help improve a colony's breeding performance. Also, altering the fat content in the diet fed to breeders can improve breeding performance. Some mice will breed better if you increase the amount of fat in the diet, whereas other mouse strains breed better if you decrease the amount of fat in the diet. Adding enrichment is another way to improve breeding performance. As an example, mice see the plastic dome show up here as opaque, so they behave as if they are sheltered or hidden when in the domes. Shelter enrichment such as domes can encourage breeding by helping breeder mice feel safer and less stressed. Later in this presentation, I will discuss data from studies we performed to assess enrichment options for improving breeding efficiency. Finally, we recommend keeping breeding pairs together. Removing the males when the females are pregnant or when the females give birth can be stressful to the females and result in the mothers either aborting or resorbing embryos or not caring well for the pups. Shortly after female mice give birth, they go into estrus, which is known as postpartum estrus. By keeping a mating pair together, the male and female can breed again, and then shortly after the first litter weans, the second litter will be born. By keeping mating pairs together, you can improve the efficiency and output of your breeding colony, as well as conserve space because you won't have to house the males in a separate cage. The Jackson Laboratory has been breeding mice for over 90 years and has found that rigorous data collection and record keeping is absolutely critical for successfully managing your colonies as efficiently as possible. Breeding data provides a wealth of information that can be used to optimize breeding productivity and ultimately help ensure you have an adequate supply of experimental mice when you need them. Rigorous breeding data collection and routine analysis of that data also enables early detection and assessment of potential problems or mutations in a colony so that issues can be addressed as quickly as possible. This graph shows 6 years of breeding performance data for 4 of our mouse strains, C57 Black 6J, AJ, NSG, which is an immunodeficient strain, and BALB-CJ. The data shows that breeding performance for these individual strains is not consistent over time, which is going to be the case for virtually every mouse strain. In order for us to maintain our colonies as efficiently possible, we are regularly monitoring strain breeding performance on a weekly, monthly, and yearly basis. We use the data collected to optimize breeding colony efficiency and ultimately to produce the quantity of high-quality mice needed to supply the needs of the global research community. At the heart of efficient colony management is rigorous data collection. In the past, a pedigree book, which was literally a book, served as a critically important record of colony breeding performance and data. Currently, electronic systems, databases, or spreadsheets are used to record, monitor, and analyze breeding performance data, thereby enabling assessment of a past and present colony's breeding performance. Important information to maintain for each strain includes nomenclature, genetic background, and strain history, which is basically all the information you can obtain about the mice before you receive them, as well as records of everything you've done with those mice. For example, backcrossing, intercrossing, cryopreserving, etc. Other important data to record include unique animal numbers, used for tracking mice used in your experiments, and all the breeding information related to each of your colonies. Keep records on all mice you use for breeding, including but not limited to breeding pair mating dates, litter-borne dates, litter sizes, pup weaning dates, the number of pups born, the number of pups weaned, the sex of the pups born, and the sex of the pups weaned. When breeding a segregating colony, record all of the genotypes of the pups so you know what percentage of mice produced are of the genotypes needed. Monitor wean per pen, which is a measure of the breeding performance of your colony. Wean per pen is calculated by dividing the total number of weaned pups by the total number of breeding pens over a given time period. Any significant changes in the wean per pen ratio should be investigated to assess a possible problem with the colony or the breeding environment. We recommend tracking the sex ratio of your colony in order to more accurately forecast the number of males and females that should be available for experimental use. We also recommend monitoring for changes in sex ratio, which could indicate a problem in the change in the colony. Tracking genotype ratios is also important. For example, if you're using a heterozygous by heterozygous breeding scheme in your colony to produce homozygous mice for experimental use, and that colony's homozygous genotype ratio drops, say from 25% to 20%, that's something you want to investigate the cause of the decline by reviewing the colony records and then potentially adjust the size of your colony so it will produce an adequate number of homozygous mice for experimental use. Now I'd like to share with you some helpful tips for record keeping. Using printed cage cards or labels versus handwritten ones helps ensure that the cage information is legible for all who are working with the mice and thus helps avoid mistakes due to misreading or misinterpreting such important information. Using cage cards of different colors to visually distinguish adjacent strains helps avoid inadvertently mixing up cages of different strains. Or the different colors can distinguish the mating pens from pens with experimental mice. It is best practice to maintain mouse strains with similar names, whether the formal strain nomenclature or the shorthand name of the strains, in separate locations. For example, C57 black 6 mice and C57 black 10 mice have very similar names. Keeping colonies of these two strains in separate locations of your mouse room will help avoid inadvertently mixing up cages of these two different strains or accidentally crossbreeding them. Another helpful tip is to maintain all the breeding and weanling cages for a single strain in the same location with visually differentiated cage cards so that you can monitor the colony as a whole, more easily track all of the cages for that strain, and more efficiently gather and record colony performance data. It is also important to keep records of your colony in multiple locations to avoid the risk of losing records or losing access to those records in the event of a computer or internet outage or of a natural disaster. Even if you are using electronic record keeping systems, maintaining and archiving physical cage cards can help with investigating and resolving unexpected data discrepancies or breeding issues. For tracking generation numbers, N is used to reference the number of backcross generations. N refers to how many times a strain has been backcrossed to an inbred strain like C57 Black 6J or BALB-CJ. F indicates the number of brother by sister matings or inbreeding generations. P is used to indicate a point at which a strain was cryopreserved. And at the Jackson Laboratory, we use the plus sign to separate the generation information for a strain prior to importation into the Jackson Laboratory from generation information for that strain once received at the Jackson Laboratory. For strains received without information from the donating investigators, we use a question mark to indicate that lack of information. So for this example, N6F12 indicates 6 back crosses followed by 12 inbreeding cycles or brother-sister matings. And then Jax imported this strain and did an additional 8 brother-sister matings. For this example, Jax imported the strain, but we don't know the generation of the mice we received. And then we performed 10 back cross generations followed by 5 brother-sister matings. And you can work out the other example if you wish as well. To help ensure that you understand generation nomenclature, let's work through this question together. Let's say you have received mice from a collaborator and have been inbreeding those mice by brother-sister matings for 6 generations. What would be the generation number that you would use in the nomenclature for this strain? Option A is F6, B is question mark plus F6, C is N6, and D is question mark plus N6. And E, the answer is not listed. Since you have conducted 6 brother-sister matings, which are designated with an F, and N, which refers to back crossing, should not be used. So therefore, answers C and D are incorrect. The correct answers will be A or B, which both include F6. In this example, since mice with an unknown generation number were received from a collaborator, answer B, which includes this question mark indicating an unknown generation number, is a bit better. If you do obtain mice from a collaborator, we highly encourage you to obtain breeding history information from the collaborator in order to have knowledge about the underlying genetics of the mice, to record breeding history of the strain for future reference, and to reflect generation information in the strain nomenclature. At times, you may need to identify individual mice either for tracking their pedigree for breeding purposes or for an experiment so that you can collect and correlate data on an individual mouse basis. Options for identifying neonatal mice are somewhat limited. You can use a tattoo with an appropriate pigment to imprint 2 letters or numbers on the tail of a neonatal mice. We recommend discussing other options such as toe clipping for identifying neonatal mice with your Animal Care and Use Committee and your veterinary staff. More individual identification options are available for weanlings or adult mice. You can use an ear notching system, ear tags, surgical markers, or microchip implants. A common way to identify individual mice with ear notching is to use the right ear to indicate the 1s and the left ear to indicate the 10s. A hole punch in the top, middle, bottom of the right ear correlates to 1, 2, and 3. And in the same pattern of holes in the left ear correlates to 10, 20, 30. A notch in the top, middle, and bottom of the right ear correlates to 4, 5, and 6, and the same pattern of notches in the left ear correlates to 40, 50, and 60. A double notch in the top, middle, and bottom of the right ear correlates to 7, 8, and 9, and in the left ear correlates to 70, 80, and 90. This system then allows for identifying up to 99 mice. To help ensure that you understand this ear notching system, let's work through the identification number of the mouse pictured here. The notch in the middle of the left ear codes for 50. The punch in the right ear, bottom of the right ear, correlates to 3. So this mouse identifications number would be 53. There we have that. A more qualitative system can be used to identify progeny by genotype and by sex from a colony with a segregating mutation or transgene. For example, you can use 1 hole punch in the right ear, 1 hole punch in the left ear, 1 hole punch in both ears, 2 hole punches in the left ear, 2 hole punches in the right ear, etc., which is a system you can use if you need to identify mice for a shorter period of time, say just until you get the genotypes, and then you're going to maintain your colony based on their sex and genotype. As mentioned earlier, the ideal age to mate mice is strain dependent and should be determined empirically. As general guidance, we recommend setting up your breeding units when the mice are between 4 to 12 weeks of age. Mice that are 12 weeks of age, over 12 weeks of age, may not breed as well as younger mice or sometimes will not breed at all. Mice used for breeding should be chosen carefully in a manner that avoids any sort of selection pressure, especially based on breeding performance. You might think that if some breeding pairs breed better than the average breeding performance of your colony, then why not exclusively use those breeders and their progeny for further breeding to improve the overall breeding performance in your colony? However, selecting breeders based on superior breeding performance may also result in selecting breeders that also carry a mutation or some other modifier of the phenotype of the strain. To avoid inadvertently altering the phenotype of your colony by selecting for good breeding performance, it is best to randomly select your breeders rather than choose breeders based on breeding performance. To optimize the productivity of your breeding colony, breeders should be replaced on a regular rotation. As an example, let's say you have 6 mating pairs in your colony and a 6-month breeding rotation. Ideally, the breeder pairs in this colony should be a month apart in age, and every month the oldest breeder pair should be removed and replaced with a younger breeder pair. A mixed age colony provides more consistent breeding performance over the life of that colony and minimizes the number of young breeders needed at any given time. If you're replacing one breeder pair every month, you only need to have one additional pair available every month, versus replacing all 6 of your pairs at the same time. You can also improve the productivity of your colony by replacing any non-productive breeders as soon as possible. As a general guideline for most of our strains, we allow 60 days for a breeding pair to successfully wean a litter. If a breeding pair requires more than 60 days to produce and wean a litter, then we typically replace that pair with a younger breeding pair. However, if we know that that specific strain is a poor breeder or are slow to start breeding, we might give them 90 days for a breeding pair of such a strain to wean a litter before we would replace that pair with the younger breeders. The timing for replacing breeders is guided by the breeding data collected for each strain, which highlights the importance of rigorous record keeping. To safeguard the genetic integrity of mouse strains that are critical to your research and are bred in large colonies, you may want to maintain a pedigreed colony using only brother-sister matings. A pedigree colony consists of a single colony with multiple pedigree lines. In this case, there are 2 lines, pedigree 1 and pedigree 2. Each pedigree line is maintained by brother-sister matings within the line for every single generation. Mice from pedigree 1 should not be mated to mice from pedigree 2 or vice versa. Keeping separate pedigree lines enables having a backup if one of the pedigree lines develops a spontaneous mutation. If a pedigree line develops a spontaneous mutation, it should be removed and replaced with a newly established pedigree line so that at least 2 pedigree lines for a critically important strain are being maintained simultaneously. Pedigree colonies can be instrumental in minimizing and eliminating spontaneously arising mutations in breeding colonies and in limiting the number of mice in a breeding colony that may be affected when a spontaneous mutation arises in a colony. It is important to replace the breeders used in pedigree lines so that no mice in your colony are more than 10 generations from the original stock to prevent generating substrains in a breeding colony. Colonies of breeding lines can be refreshed by introducing new breeders derived from the original stock of that strain, at least every 10 generations. There are multiple options for setting up matings themselves. The simplest mating approach is a pair, 1 male and 1 female housed in 1 cage. Mice can also be set up as trios for mating, which consists of 2 females and 1 male housed in the same cage. For some strains, trio matings can be more productive in terms of the wean per pen due to the aunting phenomenon. Aunting can happen in trio mating when one female gives birth to a litter before the other female, and then after weaning its litter, that first female to give birth then helps care for the other female's litter. Aunting can help improve the overall breeding performance of your colony. Another advantage of trio mating is that housing the trio breeding units requires less cages in the mouse room, so saves space and animal care time. Harem matings, which consist of a single male with more than 2 females, are also an option for maintaining a breeding colony. I've heard of up to 6 females being used in harem matings. We tend to avoid using harem matings in our facility. We have found that harem matings can reduce the sperm count in the male so that while he may physically breed more frequently, he may not be as productive. Also, sometimes if there are too many females in a cage with a single male, the female sometimes will fight with the male and prevent him from breeding at all. For situations where you have a limited number of males and a need to breed those males as much as possible, male rotation is a possible breeding option. Male rotation can be accomplished by mating a male with 2 females for a week and then moving that male to a cage with 2 new females for the next week, and then continuing to mate that male in trio matings with new females for each successive week. Male rotation can be useful when starting a colony with only a few males available. Also, rotating males can be useful for strains that have a very short lifespan by maximizing the amount of breeding that can occur within a limited time frame. If the breeding performance for a colony is very poor and the females are struggling to successfully wean litters, using foster mothers to better care for the pups is an option to improve pup survivability. Using fostering can help provide more robust weanlings to build or expand a colony or to use in experiments. Selecting ideal foster mothers involves choosing experienced foster moms that have already successfully weaned a litter. The foster mother should have a litter that's as near in age as possible to the litter that needs to be fostered. The foster mother usually has to be within 1 or 2 days, older or younger, of the age of the litter to be fostered. If possible, the foster mother should have a different coat color than the pups to be fostered, so coat color can be used to easily distinguish the foster mother's natural progeny from the pups that need fostering. After selecting an appropriate foster mother, the next step is to remove the mother's natural litter and reduce it in size so that the total number of pups that need to be fostered plus some of the mother's natural pups will be equal in number of the pups in her natural litter. For example, if she had 8 pups in her natural litter and 5 pups need to be fostered, then 5 of her natural pups need to be removed and 3 of her own pups need to be combined with those 5 foster pups so that the combined litter that is given back to the foster mother is the same size as the mother's original natural litter. As a next step, gently mingle the foster pups and natural pups with the soiled shavings from the foster cage to transfer the foster mother's scent on the pups, and then put the combined litter in the cage with the foster mom and leave them alone. Give the foster mother a chance to gather all the pups in the nest. Milk spots will indicate if the pups are being properly nourished and cared for by the foster mother. I'd now like to share some data that we collected with guidance from our internal Animal Care and Use Committee for a study to assess optimal cage density of our breeding colonies. We performed this study to ensure the health and well-being of our mice, as well as to possibly uncover opportunities to improve mouse production efficiency. This study included 3,300 breeders in 1,300 plus breeding units and was conducted at our facilities in both Bar Harbor, Maine and in Sacramento, California. 7 different mouse strains were included in this study, 4 common inbred strains, C57 Black 6J, Balb CJ, DBA1J, and AJ. We also used 2 different F1 hybrid mouse strains and the highly immunodeficient NSG mouse strain. We compared breeding pairs versus breeding trios in our duplex cages, which are shown here, and in the weaning cages, which are shown here. A weaning cage has the same overall footprint and volume as the duplex cage, the difference being that the weaning cage has 1 compartment, whereas the duplex cage has 2 equally sized compartments. Only 1 breeding pair or 1 breeding trio can be housed in a weaning cage, which has 1 compartment, whereas 2 breeding pairs or 2 breeding trios can be housed in a duplex cage, which has 2 compartments, each half the size of a breeding cage. Therefore, housing breeding pairs and breeding trios in duplex cages doubles the density of mice per compartment as compared to the density of the same number of mice housed in weaning, the 1 compartment cages, which have the same footprint as the duplex cages. For this study, we collected breeding performance, pup weight, and pup mortality data for the mice housed in both the weaning cages and duplex cages. Overall, the study data indicating that increasing the density of breeding trios and pairs by housing them in the individual compartments of the duplex cages had no negative impact on the mice. Specific findings from this study included the following. The weaning weight of pups from trio matings was higher than the weaning weight of pups from pair mating in both types of cages. There was a marginal increase in the total number of litters born per female when mated in pairs as compared to mated in trios. The number of pups weaned per cage was greater for trio matings than for pair matings, but the pair mated females produced more pups per female. There were slightly fewer pup mortalities per breeder female from cages of mice bred in trios, and there were fewer pups culled for defects from the duplex cages as compared to the weaning cages. Based on our cage density study, we did not find a dramatic or significant difference between breeding mice in compartments of a duplex cage as compared to breeding in a weaning cage, which provides twice the housing space of a duplex cage compartment. In summary, this study demonstrated that breeding mice housed in smaller cages did not negatively impact the health, well-being, or breeding performance of the mice. If you are interested in learning more about the impact of housing density on breeding mice, I encourage you to watch a video recording of the Jackson Laboratories presentation dedicated solely to that topic. This video includes a more in-depth review of all the data in our mouse density study, as well as data collected by other researchers around the world who study the impact of density on breeding performance in mice. Please use the email address on the last slide of this presentation to request a link to the video. As another means to ameliorate strain-specific breeding and husbandry challenges, JAX uses enrichment, which can improve the health, well-being, and breeding efficiency of some of our mouse strains. Let's discuss the impact of using enrichment for two of our strains, C57 Black 6J and SJLJ. C57 Black 6J mice have issues with barbering, which tends to be more frequent with female mice that are group housed together. Barbering often involves whisker picking, hair loss, and alopecia. You can see the phenotypes here where the mice are actively pulling out the hair and whiskers of their cage mates, which leaves bald patches. This behavior tends to be more frequent as the mice get older and as the density of the mice in the cage increases. Barbering is believed to be in part to be caused by social dominance behavior resulting from mice over-grooming each other as part of their social interaction. Additionally, this behavior could be due to stress or some sort of obsessive-compulsive disorder. As a means of mitigating barbering, we ran a study to assess the impact of using different types of enrichment in cages of C57 Black 6J mice. Our goal was to identify enrichment that would reduce the amount of hair loss in our C57 Black 6J mice, thereby increasing their health and well-being. For this study, we set up 3 groups of mice with more than 1,000 females in each group. The control group had no enrichment. One group was provided shelter-type enrichment, which included cardboard tunnels or cardboard domes. Third group was provided with activity enrichment, which included trapezes or rings to encourage mouse activity. During this study, we continued to use all of our standardly used other husbandry practices. We then monitored the mice from 3 to 12 weeks of age for hair loss and other adverse signs. And the data showed a significant decrease in the percentage of mice with hair loss when provided shelter enrichment as compared to being housed with no shelter enrichment or activity enrichment. Based on this study data, we now include shelter enrichment in all of the breeding and weaning cages for C57 Black 6J mice. The result of this change has been a reduced number of mice with hair loss. The benefits of this change are that the C57 Black 6J mice shipped to researchers have improved health and less hair loss, and that the efficiency of our C57 Black 6J breeding colony has improved. We also ran a study to assess the impact of enrichment on mitigating the aggressive tendencies in the SJLJ mice. SJLJ males are highly aggressive to both their mates and their pups, which can result in either bite wounds or death of those mates or pups. As you might imagine, this aggressiveness can negatively affect the breeding performance of SJLJ mice in terms of pup survival, total number of litters, and the time frame for the females to produce their first litter. The aggressiveness of the SJL males tends to increase with age and caging density. And we ran a study to compare different types of nesting enrichment to see if any could potentially alleviate the aggressive tendencies of the SJL males and ultimately to improve their breeding performance. The enrichments used in this study includes nestlets, which are paper products that can be torn up and made into nests, aspen shavings, product known as Viro Dry, and another product called Alpha Twist. We supplemented our regular aspen chip bedding with one of those 4 different nesting materials, and then assessed productivity and welfare parameters measured throughout a standard 22-week breeding rotation. All other standard husbandry practices remained unchanged. The resulting data showed that 2 of the testing enrichments, the Alpha Twist and the EnviroDry, significantly improved breeding productivity in SJLJ mice. Here are some of the data details related to using enrichment in cages of SJLJ mice. Pups' survival increased with the Alpha Twist and EnviroDry. The average number of litters per female also increased, and the average time to produce the first litter was reduced with both Alpha Twist and EnviroDry. Now, since Alpha Twist had the most positive impact in all of the testing enrichments, we now use Alpha Twist in all of the breeding boxes for our SJLJ colony. The addition of this enrichment has improved the mouse health, well-being, and breeding performance in our SJLJ colony. Now, let's discuss some approaches to reducing the cost and facility space used to maintain your mouse colonies, which result in optimizing efficient use of your animal care resources. First, size your colonies to produce the numbers of mice that you need when you need them. Planning and implementing a breeding plan to size your mouse colony to best meet your needs and to minimize wasting resources and unused mice requires rigorously maintaining, monitoring, and analyzing your strain's breeding performance records. Another approach to reducing colony management resources is to use both sexes of mice and/or an age range of 2 weeks or more in your experimental studies whenever possible. Using mice of only one sex or only mice all born in the same week requires a much larger breeding colony, which incurs more resource usage and costs. If you are using commonly used inbred mouse strains like C57 Black 6J or Balb CJ that are readily available from JAX or other research mice suppliers, ordering such mice as needed may be more efficient than maintaining your own colony, especially if you need to use only one sex or need a very tight age range. It is important to set up a well-organized structure to maintain and establish a mouse colony. Employ an experienced mouse colony manager to oversee the breeding performance and efficiency of your colonies and to minimize the space and resources used to maintain your mice. We advise that mouse colony and facility managers work closely with veterinary staff to monitor and ensure the health and welfare of your mice. Also, we encourage you to consider cryopreserving any strains that are rarely used or unique strains that would be difficult or costly to re-engineer in the event of a breeding cessation of that strain, or pathogen outbreak in your facility, or natural disasters like fires, floods, earthquakes, worldwide pandemics, etc. Cryopreserving strains eliminates the cost and space requirements of maintaining live colonies. We invite you to use our cost-saving calculator that is accessible online to estimate cost savings realized by cryopreserving a mouse strain and no longer supporting a live colony for that strain. The cost of JAK sperm cryopreservation is economical and offers significant advantages as compared to traditional methods used for cryopreserving sperm. We now cryopreserve sperm for most of the mouse strains imported into our facility because doing so is more cost effective as compared to embryo cryopreservation. Cryopreservation is a key component of our patented genetic stability program, which we also know as GSP, which we use to limit genetic drift in many of our large production colonies that support commonly used strains such as C57 Black 6J, BALB-CJ, and NSG. GSP involves cryopreserving a 25-year supply of embryos that are all from the same generation for each strain in the program. We then cryorecover some of those embryos to generate live mice to be used as breeders in the GSP strain's foundation colony. We breed foundation colony mice for at most 5 generations, at which point we then remove those breeders from the foundation colony and replenish the foundation colony with new breeders generated from cryo-recovered embryos from the 25-year cryopreserved embryo supply for that GFP strain. Some of the breeders used in a strain's foundation colony are transferred to and used as breeders for that strain's expansion and distribution colonies, which produce the mice shipped to the worldwide research community. Mice in the expansion and distribution colonies are at most 10 generations removed from the foundation colony. Therefore, any GSP strain from the Jackson Laboratory are at most 15 generations removed from the 25-year cryopreserved embryo supply for that GFP strain. A GFP strain may develop new mutations during those 15 generations of breeding, but those mutations will be bred out of the colony because we systematically reinfuse the colony with new breeders generated from the cryopreserved embryo supply for that strain. As a result, the JAX mice received from us today will be genetically equivalent to mice received from us 5 or 10 or 20 years from now. I'd like to conclude this presentation by summarizing some key points. Know the breeding history and breeding characteristics of each of your mouse strains. Practice rigorous record keeping and routine review and analysis of colony breeding data to support efficient colony management and optimize colony output. Quickly investigate and address any changes in breeding performance in your colony to avoid compromising the quality of mice from your colony and to ensure an adequate supply of experimental mice from your colony. Consider using both sexes or a wider age range in your experimental mice to maximize the use of all available progeny from your colony. And cryopreserve rarely used strains to minimize use of resources needed to support live colonies of mice. Cryopreserve unique strains or any strains for which you want a backup supply in the event of a pathogen outbreak at your facility, unexpected breeding cessation, or natural disaster. Now I would like to just mention that this webinar was made possible with your support. JAX Mice Clinical and Research Services staff are dedicated to providing you with quality resources, flexible solutions, innovative technologies, and unsurpassed expertise and support to accelerate all aspects of your research. Your investment in our services and mice supports our shared research goals and helps sustain valuable mouse models and resources that are available only from the Jackson Laboratory. In addition to our commonly used inbred strains and unique mouse models, we offer a wide array of services to support your research goals. We supply steady, ready aged C57 Black 6J mice. We can breed and maintain your mice for you or support your needs for model generation. We can cryopreserve your mouse strains, recover cryopreserved strains, and then perform in vivo efficacy testing for preclinical research for you. If you need help with a service, please reach out to us using the contact information on the final slide, and we'll discuss how we can work together to advance your research. And with that, I want to thank you very much for watching this video today. I hope that this presentation has provided you with valuable information to help you achieve your research goals. If you have any questions about the information that I shared with you today, please contact us using the email address micetech@jax.org on this slide. We would be delighted to support you with our technical assistance.